we'll get started.
Yeah.
Used to have Dr. Manami Roy here from Ohio State University. She got a PhD in 2023 from the Raman Research Institute in India. And then she landed this postdoctoral fellowship at Ohio State University. And she studies the circumgalactic medium, meaning the gas around galaxies. So it's hard to study that. That's the thing that is very, very difficult to observe in many ways. So it's a challenge. So yeah, so now she's at OSU at the Center for Cosmology and Astroparticle Physics. Thank you so much for coming and sharing your wisdom and knowledge with us. We will. Is it okay if we ask questions during the talk?
Yeah, it's absolutely fine. Yeah.
Yeah, thank you. So,
Yeah.
So if you have a question, go ahead and shout it out. I think you have to be relatively vociferous in order for it to be heard.
So, can you see my screen, right?
Yes.
Yeah. Okay. Thank you so much for having me, and I'm very excited to join all of you today and share some of my research with all of you. So today I'll be talking about very high energetic relativistic particles, cosmic rays, and how they play an important role in the evolution of the galaxies. But before jumping into that, let's start with a very basic question that what is a galaxy? So when we imagine a galaxy, we think something just like this, and what we are looking at here is billions and trillions of stars which are emitting lights, and in between stars there are this gas and dust. You can see the dust lanes around the spiral arms of the galaxy, and this type of galaxy is known as spiral galaxy because obvious reason, because these are having like spiral structure, spiral arms. But telling somebody what a galaxy is something like telling somebody what a cat is and showing one picture of the cat, and which possibly cannot cover the wide variety of cat we have in our universe. And sorry if you are a dog person, it's also similar story for dogs. So in that regard, this recent JWST picture actually amazed me because it captures this wide variety of galaxies in this small patch of the sky. And so in the screen, all of the dots you are seeing are galaxies, and except for I think 3 of them, they are stars. And they come in all shapes, sizes, colors, and ages. So it's very difficult to categorize galaxy in one aspect. But one of the categories astronomers keep coming back to are blue and red galaxies. And what do we mean by blue and red? And you can see a lot of blue points and red points in the screen as well. So blue and red galaxies are telling us whether the galaxy is forming stars or not. So on the basis of star formation, astronomers classify galaxies. So star forming galaxy or quiescent galaxy. Now, in order to form stars, galaxies need cold gas. But if you count all the gas in the galactic disk in between the stars, you can find that galaxies actually don't have enough gas in their galactic disk to continue star formation for a long period of time. And for our own galaxy, Milky Way, you can actually calculate this, and you know the gas mass of the Milky Way, and you know the star formation rate, and you can calculate the time scale by which the fuel for the star formation or the cold gas will be depleted, and it will come out 2 to 3 giga-year. But we know that Milky Way is forming stars more than that. So what's happening here? So where does these galaxies are getting star formation fuel, like this gas? So far, I have been misleading all of you about what is a galaxy is. I was showing you the picture, which are easily available, I was showing you the picture of the star forming optically visible central part of the galaxy. For our Milky Way, it's 10 kiloparsec in the central region. And because it has all the stars which emits bright lights, so we can easily see this small part of the galaxy, central part of the galaxy. But official size of the galaxy is much bigger, even like 10 to 20 times bigger than this central bright part of the galaxy. So in this official size of a galaxy is roughly of the size of how big their dark matter halo is, or roughly speaking is the size of the virial radius of a galaxy. And in this dotted line, it contains invisible dark matter, which is literally invisible. We can't see it. And then there is invisible in quote galactic atmosphere or diffuse gas, which is known as circumgalactic medium. And technically, it is not invisible, but it is very diffuse. It has very low density, so it doesn't emit in the sensitivity that we can observe with our current telescopes. And to give you a size estimate for our Milky Way galaxy, our Milky Way CGM is like 250 kpc, roughly. So which is like 20 times, even more than 20 times bigger than the central optically visible galactic disk. So now you can ask me, if it's so diffuse gaseous halo, then why it is so important for us to study it? CGM is very important because this atmosphere or this diffuse gas is continuously talking to this central part of the galaxy with through this gaseous exchange. So they are doing inflowing of gas, outflowing of gas, recycling of gas, all this gaseous exchange with this central part, star forming part of the galaxy. And by these processes, it can supply star formation fuel to the central part of the galaxy, and using those star formation fuel, it can form stars for a long period of time. So it actually answers our question that where does galaxy get this star formation fuel in order to keep forming stars? It's from this diffuse gaseous halo around these galaxies. So CGM is very important for galaxy evolution. Now you might ask me another question, that how do you know that this thing exists if you can't see it? It can't emit lights. It can't emit light in the sensitivity of our current telescopes. So how can we know that it exists? Thanks to the absorption line spectroscopy, which is if there is a bright background source, typically it's a quasar, and the light or the continuum emission from these background source, when it passes through a CGM or circumgalactic medium of any galaxies, it suffers absorption from different ions which are there in this galactic atmosphere or CGM. And by looking at those ions, you can actually tell the temperature, density, and different properties of the gas of those regions of the galaxy by which this sightline passes through. So, and we have so many quasars in background quasars and so many sightlines. And by studying all of these absorption lines, we actually now know this CGM, this diffuse gaseous halo, is multiphase in nature. And what do I mean by multiphase? It has a lot of temperature because it actually shows this absorption lines from a wide variety of ionization potential, like very low ionization potential of magnesium 2 to very high ionization potential of silicon 14. So for example, you can actually have very cold phase of less than 10 to the power 4 K, which is stressed by magnesium 2, silicon 2, and you can have a volume filling warm hot phase, which is roughly of a temperature of virial temperature of a galaxy, which is for our Milky Way is 2 times 10 to the power 6 Kelvin, which can be stressed by O7, O8, these ions. And then there is this fourth category, which is very high, even hotter than the virial temperature of a galaxy, greater than 6 times 10 to the power 6 K for Milky Way. And for Milky Way, it has been detected recently by neon 10, silicon 14, which are very high ionization potential ion. And this is the gas even hotter than the virial temperature of the galaxy. This is called supervirial phase. So usually we categorize this multi-phase CGM into these 4 different phases. Now the key questions related to this multi-phase diffuse gaseous halo circumgalactic medium is how much mass exists is in each phases, and how do these phases form, and where are these phases located, because as we're looking at the absorption column, we are actually looking at the line of sight integration of a phase. So we don't know where actually this phase is located. So where is this phase located? What is their physical extent? And how do these different phases, they're all there in the CGM. So how do they interact with each other? And is the gas in the CGM the answer to the missing baryon problem? So these are the questions people are generally interested in our field. Now, my student and I are interested in this very recently detected supervirial phase. And by looking at X-ray absorption lines from Chandra, and also by looking at idealized simulation, cosmological simulations, we are trying to understand these key questions about this recently detected supervirial phase, that where is the supervirial gas, where it is located in the disk or extraplanar region or in the CGM, and how this gas is formed because it is heated into so much high temperature. Was it because of feedback like AGN feedback or stellar feedback? Is it from cosmic ray heating, or something else is going on here? And could it be some of the missing baryons in the halo? But today's talk is not about supervirial phase, and this is the story for another time. But if you are interested, please talk to me later. I'll be happy to talk about it. But today's focus is another important component of circumgalactic medium, which is this highly relativistic charged particle. And in general, cosmic rays are not formed, these charged particles are not formed in the CGM. They are primarily formed or accelerated in the supernova shock in this galactic disk where the star is forming and supernova is blowing up. Then cosmic rays are accelerated in those shocks, and then cosmic rays are transported to the CGM by different transport mechanism. Like they can stream along the magnetic field, they can diffuse out of the galactic disk, they can even lift it to the CGM by advection by the galactic outflow. So there are these different kind of transport you can consider for cosmic rays to be transported from interstellar medium or the galactic disk to the CGM. Now, cosmic ray transport and amount of cosmic ray pressure in the ISM is very well known because there are ample amount of observations which are available. For example, this cosmic ray discharged particles actually interact with the interstellar gas, and they can actually emit in different waveband, like from gamma ray to radio synchrotron. And then they also, this primary cosmic ray interact with the gas and create some secondary cosmic rays. And by taking the ratio of primary and secondary, you can actually tell that how much cosmic rays has propagated through the gas. So from there, you can actually infer about cosmic ray transport. So by these different methods, and also there is local measurements of cosmic ray spectra by which you can actually tell what are the cosmic ray elements are there, what are the cosmic rays energies and stuff. So in the interstellar medium, in the Milky Way interstellar medium to be specified, we know the cosmic ray transport and what is the cosmic ray pressure.
Manami,
yes.
very, very roughly, what are the Larmor radii of the cosmic rays in the galactic magnetic field?
Yes, I'll come to that, but Larmor radius is like 0.2 AU. I'll come to that in about 2 or 3 slides that what is the Larmor radius, but in general for 1 GeV cosmic ray it's 0.2 AU.
Nice, thank you.
Yeah. So, but ISM we know the cosmic ray transport and stuff, but in general in the CGM, cosmic ray transport is an open question because there are not enough observations, sadly, because our current telescopes, gamma ray telescopes, are not sensitive enough to detect those emissions from the CGM. There are, although, some few observations from our neighbor galaxy M31 and also some local galaxies which are also showing some gamma ray emission from the CGM of the galaxies, but it's very few, like very handful of those things are coming up in recent years. So the main questions we are trying to address, even with this uncertainty or lack of observation, that still how to constrain cosmic ray transport in the CGM, even there is this lack of observations is going on, and what are the effects of cosmic rays in the CGM. Now, coming back to the guy's question that why this problem is even harder. It's hard because there is no observations, but it's even harder because it involved a length scale which spans orders of magnitude. So as I was mentioning that any charged particle will actually gyrates along the magnetic field, and the Larmor radius or gyration radius of the 1 GeV cosmic rays is kind of 0.2 AU. But on the other hand, the scale, we are interested in the CGM scale where cosmic ray pressure acts on the ambient medium and evolve globally is kind of greater than kiloparsec scale, which is in the CGM scale. So you can see that 0.2 AU to kiloparsec, this is our range of length scale. So it's very hard to even simulate this problem. So it's very hard. Because if you want to simulate the large scale physics, you actually you have to use some subgrid model for the small scale physics. So it's simultaneously doing all of these things are very difficult. Now the question is, why, like, if the cosmic rays are important for this multiphase CGM gas, and how does cosmic ray modify this multiphase CGM gas? So with different transport physics of subgrid model, people usually simulate in the CGM scale, and some of the recent work actually showed that cosmic ray modify the multiphase gas pretty well. For example, this is a temperature snapshot of a fire simulation you are seeing here in the Milky Way type galaxy. In the left hand side, simulation is without any cosmic ray, it's a just MHD simulation, and the right hand side, it's MHD plus cosmic rays are there. So you can see visually it is different. What is different here is in the left hand side, without any cosmic rays, the volume filling phase of the CGM is hot. But on the right hand side, when you include cosmic ray, the volume filling phase became colder than the only MHD plus simulation. So basically, it actually affects the temperature of the volume filling phase of the CGM. So cosmic ray actually modify this hot phase. It reduces the temperature of the hot phase because it provides the extra pressure support to the halo. Now, on the other hand, simulations, small box simulations of thermal instability also showed that cosmic ray modify the structure of the cold gas, and not only structure of the cold gas, it also modify the thermal instability of the simulations. And you can see in the left to right, you are actually, so in the leftmost, there is no cosmic ray, and left to right, as you go from left to right, is increased amount of cosmic rays, cosmic ray pressure. And you can see that visually, the cloud sizes or cloud morphology is very different as you increase the cosmic ray in the simulation. So we wanted to ask a question that if cosmic ray modify the multiphase gas like hot gas and cold gas, so how does cosmic ray affect ram pressure stripped gas from the satellite galaxies which are roaming around in the CGM of their host galaxy? So for that, we use a suite of idealized simulation of Milky Way-like halo with dark matter halo mass of 10 to the power 12 solar mass. We have two different satellite distribution, which is one with 20 10 to the power 9 solar mass satellite and one with two 10 to the power 10 solar mass satellites. So these are the mass of the satellites like SMC, LMC-like satellites, so which are our own satellites of Milky Way. And we put them into the circular orbit between 100 to 150 kpc from the halo center. And all of these runs include magnetic field, radiative cooling, star formation, and stellar feedback. So now, what is the basic structure of the simulation? Just let's, without any cosmic rays, it's just like 10 to the power 10 solar mass satellites which are roaming in around the CGM of a Milky Way-like host. And you can see a lot of gas is ramp pressure stripped behind the satellite, and they are kind of trying to mix and then fragmented, and then they land into the interstellar medium of the host galaxy, the disk of the host galaxy. And you can see the similar thing for this other setup where we have 10 to the power 9 solar mass satellite randomly placed, and you can see the clouds are very fast getting destroyed and landing into the disk of the galaxy. Now, basic story of this whole picture is satellite galaxies. So this is one of the snapshot I am just showing just to describe what is going on there. A lot of things are going on there. So satellite galaxies are moving through the CGM of a host galaxy, and when they move through any medium, so they actually experience a force, which is ramp pressure force, which proportion to the density of the medium and velocity of the relative velocity of the satellite galaxy with the ambient medium. And when this force is larger than the gravitational pull of the satellite galaxy, it can strip gas from the satellite ISM. And you can see in the behind of the satellite galaxy, there is this cool stripped gas. And then in the cool stripped gas tries to mix with the hot CGM because of the law of thermodynamics, it will try to mix with the hot CGM. But in the mixing layer, because the cool gas has a temperature of 10 to the power 4 K, and the hot gas has a temperature of the 10 to the power 6 K, the mixing temperature would be 10 to the power 5 K. And this temperature is having a very high cooling rate. So because it is in the peak of the cooling curve, if you see the cooling curve of this temperature dependent on the cooling curve. So in this mixing layer, there is this enhanced amount of cooling happens because of this high cooling rate, and that also induces a lot of cooled gas from the host halo. So this is the two of the channels. Satellite can actually provide cold gas to the CGM of a host galaxy by this stripping process, ramp pressure stripping process. And second is this induced mixing layer cooling in this mixing layer of this cool stripped gas. So now let's see how this ramp pressure stripped clouds, which you are seeing here, are modified by cosmic rays. So by cosmic rays, we have this extra simulation setup, which basically add cosmic rays or inject cosmic rays by supernova in the host galaxy or in satellite galaxy, because both are forming stars. And then there is this usual transport model people use, like constant diffusion coefficient. Then there is advection due to the wind velocity. And then there is streaming through the magnetic field, because we also have magnetic field. Then we have 4 different cosmic ray run and no cosmic ray run. 4 different cosmic ray run with different cosmic ray pressure in the halo, from very high cosmic ray pressure, which is 0.5 p thermal, which is usually seen in interstellar medium of Milky Way, and to very low cosmic ray of 10 to the power minus 5 times thermal pressure. So we have very high cosmic ray, which is ISM-like value, and we have very low cosmic ray, and in between two medium amount of cosmic rays. We just wanted to see if the trends with the cosmic rays are systematic. So we have this 4 variation, to low to high. Now, for cosmic ray has different species like protons, electrons, positrons, antiprotons. This is a typical cosmic ray spectra you are looking at, and it has different energies as well, GeV to TeV, MeV also. But for our simulation, we are only using protons and 1 GeV protons, one single beam, because we know that GeV protons are the ones which are mostly affecting the CGM. So, but in our future runs, we will be testing the different energy beams or different species of cosmic rays like cosmic ray electrons. But for this work, we only have 1 GeV cosmic ray protons. So now I will play this movie, similar movie which I was playing before with no cosmic ray, but with cosmic ray. So left hand side is no cosmic ray movie, right hand side is with cosmic ray movie. And you can actually visually tell that those two are very different. So I'll play the movie. So you can see with cosmic ray, the clouds are getting fragmented, but for the example with cosmic ray right hand side, the clouds are actually maintaining their coherent structure and they are not getting fragmented very easily. They are maintaining their coherent structure and for a long period of time and then falling into the host galaxy. So fragmentation rate is less with cosmic rays. So, and cosmic ray clouds are also puffier. So I'll come to that. So this is the one of the snapshot. I'm just like, if the movie is hard to follow. So this is at 1 gigayear with the same simulation movie, no cosmic ray and with cosmic ray, and you are visually seeing that there are a lot of fragmentation happening without any cosmic ray. But with cosmic ray, the clouds are actually puffier, bigger clouds, and they are actually maintaining their coherent structure. They're not getting fragmented very easily like the no cosmic ray. So, and of course, I just mentioned that we wanted to see this effect is systematic or not. So we increase the amount of cosmic ray little by little. And so left to right, you can see this is an increasing amount of cosmic rays in the simulation. And you can see that low to high, there is an increased amount of a systematic increase in the size of the cloud with the increase of the cosmic rays. Now, what is happening here? So cosmic rays are actually can provide extra pressure supports to the cloud, and it actually puffs up the cloud. So that's why you are seeing bigger clouds in the case of cosmic rays, because cosmic rays are entering into the cloud and making the cloud bigger by giving the extra pressure support. So basically pushing the gas in a bigger way. So this is cosmic ray is doing, but cosmic ray is not only doing that, cosmic ray is making the cloud bigger and it's doing something else as well. I'll come to that in my next slide. So this is like qualitatively you saw the pictures, right? But quantitatively, if you want to find the size and mass of these clouds, what do you find? So we looked into this cloud size and mass distribution. So this is no cosmic ray run. So this vertical dashed line is the initial satellite gas mass. And you can see in the earlier time from 0 to 0.5 gigayear, most of the clouds are actually located at the mass of the satellite galaxy, because the stripping has not started yet drastically for the no cosmic ray run. You can see that. And then at the later time, the stripping started, also the fragmentation started as we saw in the movie. Then there is this wide distribution of cloud size and mass you can see here, right, in the later time in the left panel. But now see what is happening with the cosmic ray. So you can see with cosmic ray, initially things are very similar, which is like they are mostly crowded in the place of satellite gas mass, but in the later time you can see there is an increasing amount of size of the clouds, and you can see this these clouds are all fragmented, but on the other hand, the high cosmic ray run, the clouds are bigger in size. And not only bigger, you can see those clouds are having even higher mass than the mass of the satellite galaxy. So that means they are actually entraining more gas from the host galaxy. So what is happening here? I told you at beginning of my slides that satellite can contribute in a two-way for the cold gas. One is ram pressure stripped clouds, and another one is this mixing layer cooling in their mixing layer of this cold stripped clouds. So here what is happening, because cosmic rays are making these clouds puffier by giving them extra pressure support, they are actually having more surface to do this mixing, and that's why they are actually mixing more host halo gas and growing in mass as well. So that's why they're even bigger than the satellite gas mass. So larger clouds because of cosmic rays, and because it is larger clouds, they are growing in mass by doing more mixing layer cooling because of the larger surface area. And of course, this effect is systematic, and we test it with even mid cosmic ray and low cosmic ray. So you can see the effect kind of systematic. So increasing amount of cosmic ray is causing increasing amount of larger clouds and increased mass growth of the cloud. Now, we now know this is the cloud is bigger and cloud survives longer, and they're not getting fragmented, and they are actually growing in mass. But what is the implications in the CGM? So this is the total cold gas in the CGM, which is coming from the satellite contribution. So which is kind of, you can see that this is no cosmic ray curve, and this is total cold gas in the CGM in the y-axis, and this is the time in the x-axis. So you are seeing the total cold gas in the CGM and time evolution of this total cold gas in the CGM. And if I plot the high cosmic ray run on the top of this, you can see this total cold gas in the CGM from the satellite galaxy also increases for the high cosmic ray. This is because this stripped gas are surviving more, they are also mixing more, and they are kind of growing in mass. So it actually contributes more cold gas to the CGM. So cosmic rays not only making the cloud looks different or growth different, they are also contributing more cold gas to the CGM by enhancing the cloud mass and enhancing the cloud survival. And I already told you that this effect is also systematic. You can see as you make the cosmic ray higher and higher, you can see this effect more. Now, I told you that there is this two effects which are actually two channels by which satellite can contribute this cold gas to the CGM of a host galaxy. One is by ram pressure stripped cold gas, and another was gas cooled in the mixing layer. So we wanted to check that if our theory is correct, then gas cooled in the mixing layer would be systematically higher in the case of high cosmic ray than the no cosmic ray. And we see that effect clearly here in the right hand side. This is whatever we are plotting is the gas cooled in the mixing layer over time. So time evolution of this gas. And you can see that high cosmic ray is producing more mixing layer cooled gas as we expected than the no cosmic ray run. And stripped gas is quantitatively similar, but stripping time is a little bit different. So, and of course, this effect is systematic. I just wanted to show these are a lot of lines. So it's basically increased amount of cosmic ray is making the more gas in the mixing layer cool because it's making the cloud huge. Now, observers actually love to look at different properties. Like one of the properties people are interested in covering fraction. And for our Milky Way, looking at the high velocity cloud, people know that this covering fraction of the cold gas is extremely higher in the Milky Way, which is like 90% or more than 90%. So, and people don't know how to create so much cold gas in the CGM. And one of the way you can do it, of course, through satellite galaxies. And one of the way you can increase the covering fraction by including cosmic rays. So what we are finding here is that for even external point of view and for even for the Milky Way in the bottom panel, we are plotting the covering fraction over the time, and the black line again is the no cosmic ray run, which is producing very less amount of covering fraction for Milky Way and also for the external galaxy perspective. But with high cosmic ray, because the clouds are bigger, and you can see by looking at those movies that it is clearly bigger, puffier, and makes more covering fraction of the cloud, and it because it's surviving, it's actually also retaining there. So it produces even like 6 to 8 times higher covering fraction. And of course, it is an idealized simulation, and our satellite distribution is not realistically mimicking the Milky Way satellite distribution, but this is like a qualitatively we can say that with cosmic rays, actually, it can increase the covering fraction of this Milky Way higher. So this can be one of the way you can have this higher amount of covering fraction of the cold gas in the CGM. Now, of course, this is systematically with increased amount of cosmic ray, you can systematically see the increased amount of covering fraction, of course, with the same effect that it is making the cloud bigger and survive more. Now, let's go back to the question of if this thing, this clouds, this cold gas which are surviving there, can they feed the galaxy? Because I told you in the beginning of the talk that cold clouds from the CGM are actually um, uh, falling into the galactic disk, and they can actually feed the galaxy for the star formation, and they can actually help galaxy forming stars for a long period of time. So as we can see that from the satellite disk clouds or this cold gas are surviving, so can they make it to the disk of the galaxy, and can they feed the galaxy for star formation? So this is whatever we are plotting is the cold gas mass flux into the inner galaxy, into the galactic disk, and over time evolution of this thing. And in the right hand side, it's like integrated net cold gas mass. And whatever you are seeing here is for the no cosmic ray, the inflow rate is kind of -2 solar mass per year. Here basically more negative means more inflow, and this is like negative indicates the inflow rate. And so you can see for high cosmic ray it is significantly higher, -8 solar mass per year. So basically the gas is making it to the inner galaxy even like 2 to 4 times higher than the no cosmic ray runs. So that's interesting that the clouds are not only surviving, but they're maintaining their coherent structure, and they're making it to the inner galaxy uh, in a way that they can actually supply this cold gas from the CGM to the uh, to the to the disk of the galaxy, or to the central region of the galaxy for star formation, which is interesting because in general small clouds cannot make it to the central galaxy if it is originating from the outer part of the CGM, because it gets fragmented very easily, because the cloud crushing time actually depends on the size of the clouds. But here with cosmic ray, you can actually make those clouds survive and feed it to the central galaxy. And then this effect is systematic. In the left hand side, we again plot the net cold gas mass flux with different cosmic rays. And in the right hand side, you can see the star formation rate of the central galaxy over time. And in the initial time with cosmic rays, actually, you can see that there are a lot of fluctuation, and star formation is little less than the no cosmic ray run. And that is expected because cosmic rays adding extra feedback to the galaxy, and that can throw more cold gas to the CGM. So basically in the beginning, you expect to have a lower star formation rate. But what is interesting here, at the end of this, like around 2 gigayear later time, when this cold gas are making it to the host galaxy or central part of the host galaxy, you actually see a increase, 2 times increase in the star formation rate than the no cosmic ray in the high cosmic ray and mid cosmic ray run. Which is interesting that because this gas is not even like just making it to the central part, it is also forming stars, help them forming stars. So it's actually helping galaxies, so cosmic rays actually in turn helping galaxy to sustain their star formation, because they are making these clouds survived. Now, another thing it's interesting, which is the transport, because cosmic ray transport is something which is very uncertain. As I mentioned, that it actually involves a large order of magnitude length scale, right? So maybe the transport, if with the different transport, this effect can be different. So we wanted to test the robustness of the transport physics. And so this is the old plot which I showed you, that size and mass distribution of these clouds with high cosmic ray and no cosmic ray, with bigger clouds and more massive clouds. But when you actually have less diffusion than our high cosmic ray run, less diffusion means less strong transport, into the clouds. So we need to have the cosmic rays penetrating the clouds, which is basically less diffusion means less penetration of this cosmic rays into the clouds. You can see that this effect actually goes down. There are not enough larger clouds and not enough survival of these clouds. So that means more cosmic rays which are coming into the cloud will make this effect larger. So we tried with one high magnetic field. High magnetic field means high streaming, which is another transport of cosmic ray, where basically cosmic rays can penetrate even strongly into the cloud. So you can see this effect even is bigger. So you can see more growth of the cloud even than the high cosmic ray. So the main point is this effect is not only depend on the cosmic ray pressure, it also depends on how cosmic rays are transported into the cloud. If it's the transport is stronger, this effect can be stronger. But if transport is weaker, like for example, this is less diffusion case, this effect can go away because cosmic ray transport is not efficiently transport the cosmic rays from the background cosmic ray into the cloud. Now, constraining this cosmic ray transport, because in all of these high like larger scale simulations, you have some subgrid model for cosmic ray transport. You actually don't do cosmic ray transport like you can't resolve point to AU in a 100 kiloparsec or 200 kiloparsec box. It's computationally very for now it's computationally very expensive. But constraining cosmic ray transport, so at small scales, are also important. So there should be a separate effort to even constrain the cosmic ray transport at small scale, and we are trying to do some effort towards that as well. So there are some interesting observations by this high energy, this TV telescopes, which are actually showing some interesting or anomaly behavior than our typical GeV cosmic ray telescope, which is Fermi. So now there is this TV telescopes HESS, Hawk, which are already online, and then there is this CTA will be coming online in recent years. So these are all TV cosmic ray, TV gamma ray detection telescopes, and from there you can actually tell that these GeV cosmic rays are centered around the acceleration site of the cosmic rays, but whereas this high energy cosmic rays are not centered around the acceleration site of the cosmic rays. So this is interesting because you expect it to centered around the acceleration site because it accelerates from there. But why you are not seeing this centered around the acceleration region is very interesting, and it can actually tell you a lot about the transport physics in the local ISM region. So this is a spectral energy distribution you are seeing for a globular cluster, where basically this low energy is observed by Fermi telescope and high energy is the HESS telescope, and this high energy data is not actually coincide with the acceleration optic center. So it is actually displaced 10 to 20 parsec away from the globular cluster. So why this is displaced is interesting physical phenomena, and it actually tells us, we actually modeled it with a different physical mechanism, and it actually tells us from the displacement you can actually constrain the cosmic ray transport or diffusion coefficient in that local region. So the physical mechanism is, I can tell you in 1 minute, basically when this globe, so you can see this is a globular cluster which is moving through our interstellar medium, and when the and this is the acceleration region of the cosmic rays. And when the cosmic rays are actually emitting this acceleration region or escaping this acceleration region, usually people assume it's isotropically escaping. But if it is not, if it is anisotropically escaping through this magnitude tail, you can see this is a small cone they are escaping, then before they can cool off, basically for low energy cosmic rays, because they cool off very less slowly than the high energy cosmic rays, they cannot be isotropized. So high energy cosmic rays cannot be isotropized before they cool off, because they cool off very easily. High energy, if energy is bigger, so they will cool faster. So you can actually retain the anisotropic behavior in the acceleration region, and you can actually observe this anisotropy in the little farther down the magnetotail of this globular cluster. So, and by looking at displacement, you can actually tell about the distribution, pitch angle distribution of this cosmic rays emitting from this region. So these kind of work is also necessary, and we are doing it because it's also important to constrain cosmic ray diffusion coefficient or transport physics in the local scale. So I will end my talk by saying some of the big takeaway. One is this diffuse gaseous halo, which is like 20-25 times bigger than the central optically visible part of the galaxy, plays a very important role in galaxy evolution because it supplies gas for the star formation to the galaxy. And this gaseous halo is multiphase in nature, and cosmic rays are actually modify this multiphase structure of this CGM, but it's very harder to observe. So we are trying to run a lot of simulations to see that how cosmic ray modified the multiphase gas. And for our simulation, when we try to see how cosmic ray modified this ram pressure strip clouds in the CGM, we see that cosmic ray makes the clouds bigger in size and then make them grow more by more mixing layer cooling because there is more surface area. And it has observational implications, like it can increase the covering fraction and mass of the cold gas in the CGM. It also can increase the inflow of the cold gas into the central galaxy, and that can actually boost the star formation of the host because it can feed the central galaxy by extra survival of these cone clouds. So thank you, and I'll happy to take any questions.
Any questions? I have a warm-up question. Were there any stars in your satellite galaxies?
Yes, they're also forming stars.
Okay, and
But because they are forming stars, their star formation rate is lower, so they actually don't provide a lot of cosmic rays from the satellite galaxy. It's mainly coming from the host galaxy. So the effect you are seeing is mainly from the host galaxy because of the lower star formation rate in the satellite.
Interesting. And those stars were losing mass, presumably.
Yeah, they have typical stellar models.
Okay. Interesting. Yes.
How do we determine where does the CGM end and the ISM begin? What is the demarcation criterion?
Yeah, you actually, like, there are no typical demarcation people can do, but in general the disk is, you can know the disk scale height or disk length by the scale height of the stars or gas in the interstellar medium. So by looking at those profiles of stars and also the gas in the interstellar medium, you can actually have a pretty good idea about what is the size and scale height of the interstellar medium, and beyond that is CGM. But then the question is how far CGM extends, because then there is this intergalactic medium also is there. So that boundary is also very blurry, that where the intergalactic medium starts and where the CGM ends. But but on the depending on the metallicity and of the both of the gas, because both of the gas metallicity or temperatures are different, density is little different, so you can actually have a boundary, but that boundary is roughly people take as a virial radius of the galaxy. But I can tell you that it's not always the virial radius of the galaxy. It can be even 2 times virial radius of the galaxy, 3 times virial radius of the galaxy. It doesn't have a definite boundary. So it's a very good point.
The tongue-in-cheek answer is this is real astronomy. So if you got it within a power of 10, you nailed. Anything else? I did wonder if you could recap for us the possible alternative acceleration mechanisms to supernovae. So supernova is one.
Yeah.
And There are a few more, and I guess they're not thought to be important, but I haven't really touched on that in a while.
Yeah, I mean, mainly primarily from supernova it's coming, but there are like if there is a AGN, so AGN can also any kind of shock can actually accelerate cosmic rays. So in AGN also they can accelerate cosmic rays, and then there is this shocks in the outflow. So whenever there is a outflow, there is these small shocks are going on, even like large bubble-like shocks. There also cosmic rays can be accelerated, but because I think for our Milky Way, the supernova is the most dominant process for the acceleration of the cosmic rays. But it's usually like wherever there is shock, you can expect a cosmic rays to be accelerated.
Well, if there are no further questions, let's thank our speaker once again. Thank you very much.
Thank you for having me.
Yeah, thank you. Actually, one more thing. Were there any online questions? Let me check my Zoom here. I don't see any. All right. Good. All right. Hey, thank you so much, and yeah, have a beautiful afternoon, and we learned a lot. Thank you very much.
Thank you for having me, and thank you so much for listening to the talk. Yeah, and thank you for the wonderful questions.
Very good. Yeah.
Okay,
Okay.
okay, bye.